For the recording purpose, okay, I need the repeating here. So we still have 10 minutes, 10 minutes, So I will show you the correction on the last question on the Green's theorem. We have the tutorial 10 week 12. The last questions, the Green's theorem. Use Green's theorem. The last question, question 12. Okay, evaluate the line integral by applying Green's theorem if C is a closed path. Okay, and notice this half C. Okay, clockwise or anti-clockwise? Is it clockwise or anti-clockwise? Clockwise.
Clockwise.
Yeah. So if normally if you apply this formula, you have a 4 curve here. Let's say this is C1, C2, C3, C4. Okay, they are clockwise closed, so it forms region R here, region R. So instead of evaluate curve C1, C2, C3, C4, you have to do line integral 4 times. It will be easier we apply Green's theorem. So if this is clockwise, this formula is actually for anti-clockwise. You del or this one is for, normally we say clockwise, we double integral with del x, coefficient of your y, right? Coefficient of y. Then if clockwise, normally anti-clockwise. If this is M, this is N, anti-clockwise, okay, the line integral M dx plus N dy, so it's a double integral, and then you del x, coefficient of N, minus you del y, coefficient of M dA. Okay, this is anti-clockwise. If we have clockwise, it will be negative of the anti-clockwise answer. It becomes negative of del n del x minus del m del y dA. Negative, that's why this notion. So that's why, be careful. This question is clockwise. We should have negative of the anti-clockwise formula. Okay, once here. This one. This is clockwise, so negative of the orientation that we already done, which is del x, coefficient of y. Okay, you expand in the negative here, so become del x 2y minus 3x, minus del y, coefficient of x, which is x plus y. Okay, and then this is dA. So negative because the direction is clockwise. So it's negative of anti-clockwise direction. Then you evaluate the delta x 2y minus 3x, we have negative 3. So minus delta y 1, delta y x, delta x 2y 0, delta x negative 3x, we have negative 3. Okay, and then your delta y x will be 0, delta y is 1, so negative 1. So negative 3, negative 1, so total is negative 4 times negative, so it's 4 times of integral, because this is constant. That's why you have 4 times of double integral dA across your region R. across the region R. So the region R here is actually trapezium. So can you still remember how to find the formula for what is the area for the trapezium? H over 2, and then your A plus B. Where, let's say this is A is the length of the top, or B is the length at the bottom. So H is the height in this case. In this case, the height is 0, 0 to 0, 4, the Y is 4. So means we have 4 over 2. A is actually, I take the, you can, AB you swap, doesn't matter. So A, the length of the A is actually, the coordinate of the X is 2. So means A here is 2. Means here 2 unit. And then the bottom length is actually 0, 0, 3, 0 is 3 unit. Plus 3. So 2 plus 3, 5. So mean the area of this trapezium is 10. That's why the answer you have 4 times 10, which is 40. No need to wasting our time to use the double integral, because this notation represents area of region R. And your region R is actually the trapezium. So you use the area of the trapezium, which is the height, in this case is 4 unit, H over 2, and the A is mean A and B are the length of the parallel line there. So this is A is 2, is A equal to 3. So you calculate the area of the trapezium is 10, and then we have 4 times of this area, so 4 times 10 is 40. So the answer is 40. If you don't believe you want to use double integral, you can also prove that the area is equal to 10. And the original answer I give is negative 40, because I didn't realize that the orientation is actually clockwise. Clockwise, the answer is negative of the anti-clockwise. So the correct answer should be 40. So any question on the last question on the Green's theorem here?